Hi everyone, I welcome you all in my new video tutorial. This time we are going to discuss about how to analyze and design a continuous beam manually using IS456-2000 provisions. In this video we are going to discuss analysis methods for continuous beams and frames, and finally we will design a continuous beam by considering its flexural, shear and deflection checks. And after that we will also create the detailed drawings based on the calculations which we have done in this lecture. So in my previous video I have discussed about the load transfer mechanism from slabs to beams, and all the calculations are listed in this Excel sheet. In order to calculate the load, you just need to multiply density with area or with the depth. So let's compare the manual calculation of load distribution with ETABS software. So we have got four categories of loads. Dead load, that means self-weight of structure. This load will be automatically calculated by ETABS software. Then live load, that is imposed load we need to assign. Then we've got SDEAD, any imposed dead load which is to be added into our structure. And finally the wall load. So let's check whether the dead load calculations are okay or not. So see, along the grade 4 A and B, the dead load distribution is 0.45. So let's check in our Excel sheet. So along grade 4 AB, so the dead load is 0.45. Similarly, we can also verify our calculations with respect to live loads. So for live load it is 0.240. So here it is 0.240 in terms of triangular loading. So as you can see, the pattern of load distribution is triangular. Similarly, for SDEAD category, the load is 0.18. So it's 0.18. And finally, we need to check about the wall load. So wall loads are to be taken as 0.6. So here you can see the wall loads are to be taken as 0.6. So total load is 1.255, and the factored load, I have applied this factor 1.2 of dead load plus 1.6 of live load, and it will be 1.70 kips on each frame element. For detailed understanding of load distribution, you can refer to my previous lecture where I have discussed various methods as well as calculations which are required to calculate the loads on beams. As you can see that this is the framing plan of our structure, and we are interested to analyze and design this continuous beam along the grade 4 between A to D. So before that we need to assume the support conditions. Right now I am assuming exterior supports are fixed and interior supports are roller, and the load which we have calculated in our Excel sheet, you just need to apply that load, and the magnitude of that load is 1.570 kPa. So there are two ways to analyze structure. Either you consider a continuous beam only, in which you need to assume the support conditions as fixed, exterior and roller interior. You can also assume the exterior support as pin, but as you know that pin support does not have any moment, but in actual supports will experience either they are exterior or interior unless you provide a certain arrangement. So supports will always experience a negative moment. So assumption of pin connection sometimes becomes conservative. There is another way to analyze the structure by considering the entire frame. If you look the plan along the elevation for between A to D, so this is how the elevation looks like, and you can divide this frame into two stories. As you can see, we have got two stories here. Number one is base to story 1, then we have got story 1 to story 2. So first level the joints as shown. After that you need to divide the frame in two stories. This is for the upper story and this is for the bottom story. Now let's analyze the upper story frame first. So now we need to assume the support conditions here. So here you can assume the pin connections, because when you analyze the bottom story, so automatically you will be getting a moment from this connection. So it will give you a realistic picture of moment distribution. If you're considering the continuous beam individually and you are just assuming a pin connection here, so it will be having zero moment, but actual it will generate a moment here because this is not pin. This is actually not fixed. Okay, this could be a partially pin, partially fixed, and that moment distribution has to be done with respect to stiffness calculations. So that's why considering the entire frame gives you relatively realistic pictures of the moment as compared to individual continuous beam. So right now I'm assuming a pin connections at the joints. So assign the loads which we have computed in the Excel sheet, and the magnitude is still remains the same, which is 1.70 kip. You might be thinking that solving this frame would be a bit cumbersome, but it's not, because if you analyze, this frame is symmetrical, and if you are solving half portion of this frame, so automatically you will be getting the answers for another half portion. For example, if you are solving left hand side, so automatically you'll be getting the answers for right hand side. So you just need to solve for 4 members, 1, 2, 3 and 4, and reverse the answers on other side, and you'll be getting the answers for the right hand side portion. In this video, I will try to complete the analysis and design procedure for continuous beam only. So in my next video, I will be solving the entire frame using Excel sheets. So to analyze the structure, moment distribution method is relatively easier than the other method of indeterminate structural analysis. So this method is used for analyzing beams and frames and was developed by Hardy Cross in 1930. And when this method was developed, it was considered the most notable advances in structural analysis during the 20th century, and still this method is considered a favorite method of all structural engineers around the globe. So in this method, first you need to assume the sign convention. Typically, clockwise moments are taken as positive and counterclockwise moments are taken as negative. After that, you need to compute fixed end moments, which are known as the moments at walls or fixed joints, and you can get the straightforward formulas of fixed end moment from the book. And after that, you need to compute member stiffness factor. So stiffness factor is actually defined as the amount of moment required to rotate the end joint of beam by 1 radian. In order to compute the stiffness factor, we've got 2 cases. One is far end fixed. So if you're looking the joint B from the joint A, so far end is fixed. So in that case, so this formula is used. K is equals to 4EI over L. E is modulus of elasticity, I is second moment of inertia, and L is length of the span. Now sometimes far end is ruler and it's combination of fixed as well. For example, if you're looking at the joint A from joint B, so far end is fixed. So in this case, you will be using this formula for EI over L. But if you're looking at joint C from joint B, so that means the far end is pin or roller. So in that case, the stiffness formula is to be taken as 3EI over L. Now let's understand how this formula is used by considering this example. So now first we need to find the stiffness, member stiffness for AB. So member stiffness for AB is 4EI over L. As you can see, if you're looking at the joint A from joint B, so far end is fixed. So that's why we are using this formula, and it will give you the stiffness of 80 times E. Now, in order to compute the member stiffness for member BC, so far end is pin or roller. So this is actually rocker support. So far end is roller support. So KBC becomes 3EI over L, and it will give you 90 times E, the value of member stiffness. Once you compute the member stiffness, then you need to compute distribution factor. So distribution factor actually means how much portion of resisting moment needs to be distributed to the adjacent members. So this is to be computed based on the stiffnesses of a particular member with respect to the total stiffness of all the members which are connected to a particular joint. For example, if you can see that 3 members are connected at a joint, and each member has got different stiffness value. If a moment of 2000 Newton meter anti-clockwise is to be acted at joint A, now the question is how much moment will each member support? Now first we need to find the stiffness, which is already given in this example. So in order to compute the distribution factor, we need to use this formula, K divided by summation of K. So for distribution factor AB, that means this is distribution factor AB. So this member, how much this member will be supporting? So KAB is 4,000, and total stiffness of the members which are connected to this joint is 10,000. So there are three members connected to joint A. So each member has got different stiffness. So let's add this. 1,000 plus 4,000 is 5,000. 5,000 plus 5,000 becomes 10,000. So 4,000 divided by 10,000, that will be 0.4. Now that means 40% moment will be supported by member AB. Similarly, in order to find the distribution factor for AC, again the formula will be same. Stiffness of that particular member, which is 5,000, and the total stiffness is 10,000, and this becomes 0.5. That means 50% of the moment will be supported by member AC, and remaining 10% of the moment is to be supported by member AD. So now you just need to multiply the moment which is acting on a joint with these factors, and this will give you the actual moment that is to be supported by the members. Remember this thing, when you apply the distribution factor, if this moment is acting anti-clockwise, so in order to resist this moment, these member has to apply the moment in opposite direction, that means clockwise. This is how the free body diagrams looks like, and that's why the sign is changed whenever you solve the table for moment distribution. And finally, we have got another factor, which is carryover factor. Carryover factor means that how much moment that is carried over from pin to wall. So typically it is half of the moment which is carried over from pin joint to fixed joint. Now let's solve our case. So this is a continuous beam subjected to the loading which is shown. So first step is to find the fixed end moments. So in order to compute the fixed end moments, we have got formulas. So for each member, we need to compute the fixed end moments. First, let's compute fixed end moment for base E, BC, and the formula is minus WL square by 12, and this will give you minus 18.84 kPa. Now you will compute the fixed end moments for CB, and this will be the same formula but in opposite sign. This will give you the same answer. Similarly, we need to compute the fixed end moments for other members CE and EF. Once you have calculated the fixed end moments, then we need to compute the stiffness factor. So there are three members having the same length of span, which is 12 feet, and same loading. So member stiffness for all the members will be same, and this is to be computed by the formula 4EI over L. When there is internal pin or roller, it will also be treated as fixed because internal pin and roller also experiences a moment. So in that case, the formula will be 4EI over L, and this will give you 288 times E inch raised to 4 divided by feet. After computing stiffness factor, we need to compute distribution factor. So distribution factor BC, that means KBC, stiffness of that member, divided by total stiffness. Now as you can see, at joint B, only one member is acting, that is BC. So KBC, infinity is added due to this fixed support, because theoretically, stiffness is the amount of force required to rotate a joint by 1 radian. But theoretically, fixed support has got 0 rotation. So the amount of force required to rotate this joint by 1 radian will be infinity, because you cannot rotate this joint. So that is why the infinity is written, and this will give you the distribution factor of 0. If there was a pin joint, then this should have been 1. So similarly, now we need to compute distribution factor CB. So for distribution factor CB, we need to compute the stiffness of this member, which is KBC, divided by the summation of stiffness connected to this joint C. So there are two members connected to this joint. That means KBC plus KBE. And if you put the values, you'll be getting 0.5 as distribution factor. Similarly, you need to compute the distribution factor for all other members and joints. Once you are done with calculating distribution factor, Now you need to form a table like this, and which you need to write joint. So how many joints are there? If you count, there are 4 joints, and the name of those joints are B, C, E, and F. So just write down the number of joints. After that, you need to write members. So at joint B, there is only one member connected to this joint. So just write that the name of that member, which is BC. At joint C, 2 members are connected. One is CB and CE. So just write those 2 members. At joint E, 2 members are connected, CE and EF, EC and EF. So EC and EF. At joint F, we have got one member, which is FE. So distribution factor for joint P is 0. We have calculated in previous slide. Distribution factor for CB is 0.5, CE is 0.5, EC is 0.5, EF is 0.5, and finally for distribution factor FE is again 0 because of the fixed support. Fixed end moments computed for all the joints are written accordingly. Now you need to write out net moment at the joints. So the net moment at joints will be minus 18.84. No need to write here, because sometimes we have got different loadings along different spans. So in that case, the net moment will differ. But luckily, we have got symmetrical sections. All the loading magnitudes are same. So that is why we are getting the net moment as 0, because positive is to be generated from this side and negative is to be generated from the other side. So that's why the net moment is 0. So once you get the moment 0, so if you apply the distribution would also be 0. So we need to stop our iteration, and our final moments will be calculated by adding the columns from fixed end moments to onwards. So if you add the columns, you will be getting the values of moments as written here. So once you compute the moments, now you need to develop a bending moment diagram. So in order to develop a bending moment diagram, draw a line, mention the joints, and mention the values which we have calculated in our previous slide. And since it is UDL, now we need to join the lines by using 2-degree curvature. This is how your bending moment diagram looks like, and you have got negative moment at the support and positive moment at the mid spans. In reality, the negative and positive moment actually represents the behavior of deflection. For example, positive moment actually represents the beam will be deflected downwards, and negative moment represents the beam will be deflected upwards. So in order to give a realistic meaning to this bending moment diagram, so let's inverse this bending moment. So in this case, the positive moments are represented below the XY line and the negative moments are represented above the XY line. So this actually represents or gives you the clear picture when the load is applied in this manner, so it will try to deflect downwards. So positive moments are associated with downward deflections, and the negative moments are associated with upward deflection. Since we have computed the moments at the joints, but we are interested to know how much moments are to be generated at mid of the span. First, we need to separate a segment of a span. After that, draw the known and unknown forces. So unknown forces in this case are reaction at B and reaction at C. The moments we have already found. It's 18.84 anti-clockwise on this side, and CB is 18.84 clockwise on right hand side. Once you have drawn the free body diagram, now just apply the equation of equilibrium. Let's apply the second equation of equilibrium, which is sum of all forces along y-axis is equals to 0. So we have got RB plus RC, and the vertical force which is acting downward, that is UDL, so 1.570 multiplied by the span length, which is 12. So this is equation 1. Now you need to apply another equation, the third equation, so which is moment about point P equals to 0, taking clockwise as positive. So we have got this moment, which is BC, and then plus this force, the uniformly distributed load will also produce a turning effect, that is 1.570 multiplied by span multiplied by half of this span, and then minus RC because this will produce anti-clockwise moment. So RC into 12, and finally this is clockwise moment acting on the joint C, which is 18.84. So when you solve this, you'll be computing RC as 4.52, and once RC is to be known, just add this RC in this equation and you'll be getting the value of RP. So once you know the value of reactions, now you can find out the moment at midpoint, which is U, by applying the equation of equilibrium. So finding the moment at U will give you minus MBC, which is acting at the joint B. After that, RB will produce a moment about this point, so this will be 9.42 multiplied by. So after that, this load will be producing a moment, so 1.570 multiplied by 6 multiplied by half of the 6, and this will be anti-clockwise. And finally, RB will also be producing moment, and the magnitude will be RB into 6. Put the values, and you'll be getting MUS 9.42. So that means the moment produced at the middle of this span is 9.4. So this is the complete moment diagram of our continuous beam. So we have got maximum positive moment is 9.42 and maximum negative moment is minus 18.840. Now let's compare the values from the software ETABS. So in order to shorten the video time, I have already modeled the continuous beam, which we have solved by hand calculation. So as you can see, it is giving the similar bending moment diagram the way we have computed for our case. So let's compare the values. Yes, so the maximum negative moment we are getting 18.84 at the joint. In order to find out the moment at the mid span, which is 6 feet, and this will give us 9.42. And the similar values we have got by using moment distribution method. Now let's design this beam as per IS456. So in order to design this beam according to Indian code, I need to change the system of units. So now I have converted my values into SI system of units with the help of ETABS. So in that case, the span is 3.65 meters and the maximum positive moment is 12.77 and maximum negative moment is 25.54 kilonewton meter. So these are the cross-sectional details of our beam. Width of the beam is 152, depth of the beam is 305, and effective depth is to be calculated as 275 by subtracting cover of 30 mm from the depth of the beam. And yield strength of steel is taken as 415 megapascals or Newton per mm square, and the compressive strength of concrete is taken as 25 megapascals. So using this data, we are going to design the beam. So let's discuss the design for flexure first. So first we need to compute the MU limit using this formula 0.138 FCKBD square. By inserting the values, we'll be getting a limiting moment of 39.6 kilonewton meter. And the maximum positive moment at the mid span we have computed from bending moment diagram is 12.771. And as you can see that our ultimate moment is less than the limiting moment. So that means we need to consider a design of singly reinforced beam. So in order to compute the percentage of reinforcement at mid span, this is the formula we are going to use. So all the values are with us. By just inserting the values, the percentage of reinforcement is to be computed as 0.325. And area of steel required is to be computed as percentage of reinforcement multiplied by cross section divided by 100, and this will give us the required area of steel as 136.036 mm square. Similarly, we need to design the reinforcement for negative moment, which is 25.54 computed from bending moment diagram. In similar manner, we will be calculating the percentage of reinforcement at the support by using this formula. After inserting the values, we will be coming up the percentage required is 0.696 and the area of steel required for negative reinforcement or negative tension is 290.98 millimeters square. So final calculations are for mid span, the area of steel required is 136. So I'm using 2 bars of 14 mm dia, and this will give us the area of steel provided as 308 mm square. Similarly, for supports, the required area is 290.98 mm square, and in order to meet this value, let's use 2 bars of 14 mm dia, and the area of steel provided is 308 mm square. Now let's check the values which we have used for our design. Are they meeting the minimum and maximum specifications suggested by IS456-2000? So in order to calculate the minimum percentage of reinforcement required is to be calculated from the formula shown. insert the values, and it will be giving you 85.61 mm square. Our maximum area of reinforcement is to be calculated using the formula shown, and this will give you 1854.4 mm square. And as you can see, area of steel provided is greater than the minimum reinforcement and less than the maximum reinforcement, so that means the flexure design is okay. Now let's design for the shear. So shear force, which we have calculated from the shear force diagram, that is 18.84 kilonewton. Now we will calculate the nominal shear stress. The equations are given in page 72 of the Indian Code. So normal shear stress is to be calculated as ultimate shear stress divided by cross section, and this will give you 0.45 Newton per mm square. Now let's compute the percentage of tension reinforcement by using this formula. After inserting the values, so the percentage of reinforcement required is 0.736. Now the next step is to compute the design of shear strength of concrete, which is to be calculated with the help of table 19 given in page 73 of Indian Code. So this is the table, and this table is used based on the percentage reinforcement which we have computed. Now as you can see, the percentage reinforcement 0.736. Now let's find out the value 0.736 here. So as you can see, we don't have any value. 0.736 actually lies between 0.5 and 0.75. So we need to apply the linear interpolation. So using linear interpolation, you will be able to get out the value of shear strength of concrete at 0.736%, and that is 0.566. Now you just need to compare these two values. As you can see, the nominal shear strength is less than the design shear strength of concrete. When this is the case, that means no shear design is required. So we need to provide the minimum shear reinforcement. So minimum shear reinforcement is to be calculated using this formula. ASV divided by BSV greater than or equal to 0.4 divided by 0.8785. So ASV is considered as total cross-sectional area of stirrup plates effective in shear. So ASV we are assuming right now as 8 mm dia, 2 leg vertical steps, and for this bar size area will be 101 mm square. SV is the stirrups spacing along the length of the member. The spacing shall not exceed 300 mm in any case, so we are assuming 300 mm is spacing. So just put these values in this equation. So ASV is 101 by assuming 8 mm dia of 2-legged vertical stirrups, and B is 152, spacing is 300, and this will give you 0.002, and this value is greater than 0.0011, and this concludes the condition is satisfied and shear design is okay. Finally, we need to check for the deflection with respect to these two clauses. As we are going to design a continuous beam, for continuous beam, according to span to depth ratio, the value is given as 26. So now we need to find out the modification factor for tension reinforcement by calculating the Fs value using this expression and the percentage reinforcement which we have utilized in our tension design. So percentage of steel which we have utilized is 0.696, and Fs is to be calculated using 0.58 multiplied by Fy times AST required divided by AST provided. So AST required was 290 and we have provided AST as 308, and this will give us the Fs value of 222 Newton per mm square. Now let's match these values in the graph. So percentage of steel is 0.696, which will be coming near about here, and Fs is 222. So 222 actually lies between 190 and 240, so it will be somewhere here. So the modification factor is taken as 1.2. So the maximum allowable L over D ratio is 26 multiplied by 1.2, and that is 31.2. And the provided L by D ratio is length of our span is 3675 mm and depth of the beam is 275, and this is equals to 13.36, And as you can see, the maximum is greater than the provided. That means the beam is safe in deflection. Once all the checks are satisfied, now we need to construct the construction drawings. So in order to develop the construction drawings, this is how our continuous beams looks like. Draw the bottom bar of two 14 mm dia. Draw the top bars of two 14 mm dia and stirrups which are spaced at 300 mm center to center, and the bar size is 8 mm. Now we don't need to provide the extra bar at the supports because the bars which we provided at the top are satisfying the requirements required for the supports. So this is L section of beam along grade 4A to B. Now let's develop the cross sections at the mid span. So for cross section, as you can see, the depth and width of beam is shown. At the bottom we have provided two bars of 14 mm dia. At the top we have provided again the similar number of bars of 14 mm dia, and the stirrups are provided at 300 mm center to center of 8 mm dia. And similarly we need to draw a cross section near to the support. Every time in a beam we need to draw at least two and at most three sections. So one is at the middle of support and two cross sections near to the support. So for support cross section it would also be similar because there is no change in bar sizes and numbers. So this brings to the end of today's tutorial. In my next tutorial, I will be analyzing a complete frame using moment distribution method in order to compute the realistic pictures of moment values. And in my upcoming tutorials, I will be designing slabs, columns, staircases, and necessary structural components which are required for the design of structures. So if you find this tutorial useful, please do like and share. And if you have any doubt, you can write in the comment section. For more updates, please subscribe to my channel and press the bell icon so you can be notified on my next uploads. Thank you and have a nice day.